everyone. I welcome you all on behalf of TAIym. My name is Akshay Pawar. I'm a tunnel engineer at GeoConsult India and I'm also the vice chair of TAIym. Today we have a very special collaboration for this webinar. We are collaborating with CBTym, which is the Young Members Chapter of Brazil Tunneling Society. We have with us Alex Novak, who is a vice chair of CBTym. I welcome you, Alex. Our speaker today is Max Gabriel Barbosa, who is Technical Director, MSc at Solotrat Centro Oeste Engenharia Geotecnica Limited. I welcome you, Max. And please pardon me if I mess up some pronunciations. Max will speak on collapsible soil settlement control by grouting preliminary results for the expansion of Brasilia's subway systems. He'll share his experience of this work which he has done, and it is a very interesting topic, and I'm sure we all will be enriched in our knowledge after this. Just a couple of announcements in the start. We will take the questions from the audience in the end. So please use that raise your hand option from the Teams option bar at the bottom of your screen. Whatever questions you have, please raise your hand in the end by that option, and we will ask your questions from you one by one in the end, and our speaker will address them. And also our TAIym chair Sandeep will give some concluding remarks in the end and will share some more announcements in the end, so please stay tuned. Now I will hand it over to Alex, who will give us a bit more introduction to us, and then he will subsequently give it to Max to take it forward. So thank you all for joining. Alex, please take it from here.
Thank you very much, Akshay, for the nice introduction. We are really happy that we are doing this collaboration with TAIym. This type of collaborations is really great for us and I think for the tunneling community. Last week we had a nice collaboration as well with the Colombians in our YouTube channel. So sadly it's in Spanish, but it was really great to see, to share our experience between our groups. And I hope that we can do this here as well. We have also scheduled a collaboration with BTS-YM as well in September 3rd. And yeah, I hope this will be the first of many to come. About Max, Max is a great guy, great friend of mine. I remember we met in 2017 in the Brazilian Tunneling Congress. And I remember we shared a Uber to the airport. We have a nice long conversation. And since then, we already met in a lot of congresses and CBT events. He is a guy that has a lot of relevant works. He has a great vision of the future. And I am sure that his presentation today will be great. And I am happy that this conversation will be staying at our YouTube channels for the future, for people to watch in the future, right? So thank you again, Akshay. Thank you, Sandeep, for the meeting. And I give the floor now to Max. Thank you.
Thank you, Akshay and Alex, for the kind words. Thank you for the invitation of the Tunneling Association of India young members. And it's really a great pleasure to me to be here today, presenting to you all research we did here in Brasilia, Brazil. So everybody's seeing my screen?
Yeah.
Yes, we can see.
Okay. So I will start. the presentation of the collapsible soil settlement control by grouting, preliminary results for the expansion of Brasilia subway system. I'm Max Gabriel Barbosa, and together with the CBTym members and TAIY young members and Solotrat and the University of Brasilia, I'm presenting this talk today to you all. I will be available at the end of this presentation to answer any questions you have regarding this work and also grouting and tunnels. This presentation is divided into 6 topics: a brief introduction, some aspects of urban tunneling in collapsible soils, some aspects of soil grouting, the field grouting trials we did in Brasilia in collapsible soils for this research, and some numerical simulations for the study of the advanced length, and finally some conclusions. As we all here are tunneling enthusiasts, we love tunnels and know how sustainable and essential for metropolis and crowded cities they are. They preserve the surface, they preserve the environment, and we can have cities integrated underground with the surface reserved to nobler motives, to parks, to recreation. So we are very interested in building underground. So in Brasilia, we have a subway system, a not so big subway system. And in Brasilia, we will expand in 2021, 2022, the subway system to integrate more our underground network. And here in Brasilia is an interesting fact that we have a heritage status by UNESCO. So it's a thing I'm very proud of, but also presents challenges and also a lot of opportunities to underground work, since the surface is very expensive here. So why not build underground? Tunnels in collapsible soils are very common here in Brasilia because it's our soil here. Collapsible soils are quite similar to loess and aeolian soil. Here we have a different kind of problem. It's quite the same structure. It's a structured soil with high influence of suction and we only model this soil here using unsaturated soil mechanics and more advanced models. And the main problem with tunneling collapsible soil is because the surface settlement is very high and mainly unacceptable, except if you are building in greenfield conditions where we don't have any buildings near. Hopefully, this problem is being solved, but in the first construction of the subway here in Brasilia in 1996, it was greenfield, but we had unacceptable settlements. I will show you later in this presentation, but we had settlements of 170 millimeters in some situations, and different behavior than expected in the time when modeling by more Coulomb model. And in the time the tunnels weren't built near buildings, so it was acceptable, these settlements. But today that this expansion will be performed near facilities, near buildings, so we studied grouting for this expansion, and one of the options I will present here. We have, just for remind everybody about the most probable behavior of the tunnel face and the radial displacement, and the correlation with the direction of the tunnel advance, with minimal displacement starting about 2.5 tunnel diameters ahead of the tunnel face, the inward deformation of the tunnel face, and the radial displacement in the design and construction of tunnels by Pietro Lunardi. This is very, this is much more explained and very useful for us tunnel engineers. But here in Brasilia, as I was saying to you all, we have this problem of collapsible soils. And as you can see in this picture, we can have three kinds of soil of effect, of the arch effect. So it's a natural arch effect, a deviated arch effect, or a new arch effect. Here in Brasilia, we have a new arch effect. So when excavating a tunnel, we deconfine it, we deconfine it a lot, yeah, but mainly because the soil doesn't have the strength properties required to excavate the tunnel of, let's say, 6 meter diameter. So we have a collapse. And as I said, the Brazilian soil is a structured soil, and it's like a card castle. When you rupture one card, let's say one bridge, one clay bridge that we call here, when one bridge collapses, all the castle falls. One card collapses, all the card castle falls. Here in Brasilia, it's quite similar. So we have a very the shrinkage is very high of this collapsible soil, as in lower soils as well. So we need to avoid this situation of a new artifact. We have to build an artificial artifact in order to the tunnel to be constructed. And this can be done by conservative solutions. Here we can see a conservative line, which enables the state of stress being below the characteristic line of the soil, the C and Phi line. Of course, can be much more complicated than that, but basically we can present that conservative solutions avoid that the confining pressure goes to zero, and then creating a state of stress that the soil cannot support, and then we have a collapse that can have tragic proportions. And for this, for creating this conservative line, this improvement, and this artificial arch effect, we can have soil grouting, where we can have fracture grouting, compaction grouting, permeation grouting, jet grouting. There are a lot of soil improvement methods, but I will mainly present about the cement grout of soil. And we have to remember that cement grout is a Binghamian fluid, so it has cohesion. It's not like water or silicates or resins, which are Newtonian fluids, which doesn't have cohesion and shear resistance. And this is important in the design of these solutions, of these grouting solutions. The most famous, the most versatile, and maybe most famous here in Brazil, is the Tube-à-manchette technique, first invented by Gabriel, a French engineer, which worked for Solotrat. And this technique consists in drilling a hole, inserting a tube with valves spaced, grouting the tube to the ground, and later, after the grout hardens, injecting grouting under pressure in the valves in order to densify the soil and enhance the mechanical properties. So we can have not only a conservative effect of avoiding the decompression of the soil, but also can improve the characteristic line of the soil, the C and Phi line of the soil, by using a technique like Tube-à-manchette, like jet grout, etc. Tube-à-manchette technique is the most versatile technique, but because it can perform permeation grouting, can which permeation grouting, which is a technique that doesn't affect just permeate the pores of the soil. It doesn't alter the structure of the soil, so it's very low pressures, but has the limitation of the size of the pores. So in Brasilia, we intended to perform this trials to understand the main behavior of Tube-à-manchette here, but permeation grouting was one of the techniques that we believed it wouldn't work, since although we have a porous clay, this structured clay is very porous with permeabilities near a fine sand. It wouldn't be enough to permeate the soil with grout, maybe with silicates, which are very expensive. We can not only in permeation grouting, but compaction grouting and fracture grouting. We have two main patterns, which are the triangular pattern and the quadrangular pattern. So square. Sorry for the. It's not quadrangular. In English, is squared. So we have a triangled and a squared pattern to arrange these injections, this grouting, and we have to calculate the radius of influence of each injection. And when we perform grouting works, we measure we first estimate what improvement my soil needs. So we have a target value of improvement. I want my cohesion to increase from the effective cohesion from 10 to 30 kPa. I want to improve my equivalent friction angle from 20 to 30 degrees. We transform it in field tests values like SPT, the standard penetration test, or CPT, the cone penetration tests. And before the works, we performed this test. After the work, we performed it again and compared if the target value was possible to achieve. In this work here, where we did permeation grouting, it was possible to achieve the target value. And finally, we have fracture grouting. I believe it's the most known technique by the tunneling community, because Lord Maire in the 90s used it, in the 80s and the 90s used this technique in the Jubilee Line expansion in London. So it works for compensation grouting, where we can provide very, very high pressures, which displace the soil, as we can see here, creating lenses of grout, which in all the area treated enhance the volume, raise the volume of the area of interest, and also raise the surface. So we have, instead of surface settlements, we have surface uplift. And in many cases where tunneling create a surface settlement, it can be used to compensate the settlement by utilizing compensation grouting. But it's a technique that requires very, very specialized people, and it has worked in Jubilee Line mainly because there we had a clay which was which worked well with compensation grouting in London, but in other places in the world it doesn't. Some places work, some places doesn't work. Everyone needs to perform tests, field trials before the start of the works to see if it will really start. I believe the Professor Ada Bezoyan today is the leading expert in compensation grouting. And finally, we have compaction grouting. I don't know if you are familiar with this technique. In the US, they don't use the Tube-à-manchette. Here in Brazil, we do compaction grouting with Tube-à-manchette, but in the US, they inject, instead of stiff cement grouts, they inject concrete. So it's mainly used to raise slabs and raise pavements with very, very high pressures, but in a rate that is so slow and mainly in granular soils that create a balloon-like form, that a bulb that displaces the soil and has a similar effect to compensation grouting, but it's a technique more indicated to granular soils. And finally, the technique which doesn't use Tube-à-manchette is jet grouting, a very famous technique. We have pipe umbrellas utilizing jet grouting, but jet grouting it's a very capital-intensive technique with huge machinery and silos, and it needs more capital. So when we have time to plan and have time to build ahead with Tube-à-manchette, it become a more cost-effective solution, and that's why we chose the Tube-à-manchette technique to perform the field trials and observe the improvement in the soil and how this expansion of the subway system could be performed with greater success and without so huge surface settlements. For these executions, for these field trials, for these works of grouting, of Tube-à-manchette grouting, we utilized QC, QA, and verifications with execution control, field tests, lab tests, and monitoring of the surface to observe surface lift, surface heave, and aspects of the grout as well. This grouting was made in an experimental field of Solotrat, where we can see this reddish soil, which is characteristic of a lot of iron in presence in the soil, hematite, and we can see also a professional grouter. This experimental field was characterized in 2013 with Mendoza, and he performed triaxial tests, CPT tests, and SPT tests as well. As you can see in the first 5 meters, the soil is the typical porous clay of Brasilia, the same one found in the expansion of the subway metro and also in the construction of the subway in 1990s in Brasilia. So as it was similar and it was possible to access and it was characterized, utilized this experimental field since the Brasilia subway couldn't make an area available and the cost would be astronomically higher performing this trial there among buildings and people. So we opted for this similarity, the similar field test, the similar experimental field. Here we can see a preliminary tests where it was drilled the holes, and we were trying to assess the most effective volume per valve injected. So here we tested with 1 and 1.5, no, sorry, 2.5 and 1 bag of cement per valve. The first one on the left-hand side, we utilized 0.5 meter spacement between valves and 1 bag of cement per valve. And in the second, we realized just half a bag of cement per valve with a water cement ratio of 0.5, a very used water cement ratio because it provides a higher strength and also less problems with exudation than some water cement ratios we see mainly in the US, where they use a water cement ratio of 1, 0.8, very high water cement ratios, but have problems with exudation. So we decided to the left hand side of 0.5 meter spacement between valves and also one bag of cement with this water cement ratio of 0.5 per valve, because we could treat a bigger area and it would be more in line with our predictions. And our predictions and our field trials, we estimated a representative area. So we did these two circles here with a mean diameter, with a mean spacement of 1 meter between holes, and a 3.5 meter depth of each grouting hole, with the 0.5 meter spacement between valves and the one bag of cement per valve grouted. So we could have a representative area where we could extrapolate the results for the numerical simulations, because here we can have a representative area. We will see the improvement inside the circle and estimate and pick this improvement and put in our numerical simulations to observe the effects on the advanced length of this grouting. What will happen when we grout the surface, these collapsible soils? What will happen? So it was the main question we were trying to answer. Here are some photographs of the grouting works of the valve grouting. Here are some tests that we did to obtain the refusal pressure of the treatment. So we performed compressive strength tests of 1 day, because the Tube-à-manchette technique, we install the tube, grout the tube to the ground, and then inside the tube we inject grout, but this grout has to shatter, make little fractures in the sheath that it's the annular space between the ground and the tube, the sheath. We fracture the sheath, and we have to know the compressive strength of grouting of 1 day to size the pump, size the agitators, because with the opening of the valves can be very difficult if we keep the tube installed and the grouting hardening for more than 7 days, for example. So we have to be careful to grout in the next day, so we can use more economic pumps and agitators of this grouting, because and also to better healing of the sheath, so we can make this very little fracture in the sheath and fill it with grout after grouting. We did marsh funnel tests to assess the viscosity, and we did Lombard rheometer tests with to assess the cohesion of the grout. It's not presented here in these presentations, but it is possible to estimate the probable radius of influence of grouting by utilizing the viscosity and the cohesion of the grout, the injection pressure, the grouting volume, etc. So these tests are important to confirm that our design assumptions are correct. Here is the job after the grouting of the valves, the manchette valves. That's why sorry, not mentioning before, but the manchette, Tube-à-manchette, it's because manchette is valve in French, if I'm not mistaken, and as it was invented by a French engineer, the name was maintained. We also did geophysics to assess the improvement of the soil, but because it was very shallow, the depth of the treatment of only 3.5 meters, although we did GPR there, we couldn't assess this improvement only by geophysics. So we performed the standard penetration test. It's a very easy to perform test, and we had these logs of the work by Mendoza in 2013. So we did some tests in green. In red, we can see the arrangement of the grouting holes, and in green, we can see where the SPT tests would be performed. SPT1, 20 centimeters to F1, SPT2, 50 centimeters from F1 and 50 centimeters to F10, and SPT3, 50 centimeters to F10 and 50 centimeters for F4, and SPT4, 1 meter from F4. And we were expecting SPT2 and SPT3 to be representative of the results we will obtain field with the improvement expected. Here we can see the performing of these tests, and later we exhumed the area, we excavated to see the behavior of this grouting, because as I said before, Tube-à-manchette, depending on the design parameters, can have a permeation effect, can have a compaction effect, can have a fracturing effect. Here is very clear that we can see a bulb around some of the manchettes, and this bulb goes to we say groutability. So groutability of the soil. So where there is a lower void ratio, the grout goes. So it is very interesting because when we do numerical simulations or we design a tunnel, we usually assume that the soil is homogeneous, which is not the case. And we can, even in a quite uniform soil as in Brasilia, here, this collapsible soil, we can find discontinuities and places where the void ratio, the equivalent void ratio is lower than the global void ratio. So here we can see this behavior of compaction grouting. And also we can see near this bulb a gray area. It's not because the soil is gray. The soil was red, but because of pressure filtration, the pressure filtration is a phenomenon where the pores are clogged of the soil and just water passes, and this water has this color, this grayish color because of the cement. And so we could understand more of the behavior of grouting Tube-à-manchette with a common neat cement grout of 0.5 water cement ratio, and how this would impact in the mechanical properties of the soil. And we also did corings, as we can see in the right-hand side below. We did corings in these bulbs, in these grout bulbs, to assess their compressive strength and their mechanical properties regarding deformation. So we could assess the Young modulus by using this Humboldt machine, where we did unconfined compression tests with controlled rate of deformation and measurement of the final length of the samples. These were performed, this excavation and the zooming were performed 90 days after the grouting. So we could see quite long-term effect of the strength of the grout. And we also, in the left-hand side here, is a point load test, where a test we use a lot for rocks, and it can be also used for grouting, and it can correlate well with the compressive strength, and is a quick and cheap test. And we use that mainly to have parameters for future works in Brasilia with this grouting. Here we can see the samples after failed, after the test was done. And we obtained these results, which are very useful for numerical simulations and also for future design. We have here the grout properties when grout is fluid, the water cement ratio that I said to you, the maximum grouting pressure. This is, I'm talking about the pressure injected, grouted in each valve, not the pressure that was required to open the valve, which was similar to the compressive strength of the sheath of the annular grout around the tube. So that was the opening of the valve. It was that pressure, and then later we stabilized in maximum 800 kPa net pressure. We had a manometer in a pressure gauge near the tube to assess the real pressure that was being injected into each valve. The maximum grouting volume per valve, as I said, was 1 cement bag. It's approximately 40 liters. The exudation was still high, 10%, but as we injected a lot, it was not that a lot of problem. The unit weight of 17 kilonewtons per meter cubic. The cohesion measured by Lombardi's heliometer. Who doesn't know Lombardi? He was an Italian engineer, very famous in the tunneling and dam world. He was a dam specialist, a rock grouting specialist, and the viscosity was 150 millipascal second. The Harlan grout had unconfined compressive strength between 35 to 40 megapascals, and the Young modulus was 21 to 27 gigapascals. So it was expected, but even a little bit higher than expected. And finally, we had the results of the SPT tests, where we could see in orange, we can see the SPT4, as you recorded, it was the most in the outer circle, yeah, and SPT1 in the most inner circle, very near the F1 hole. And here we are saying that it was a 44% minimum improvement, but this is very conservative because it is compared to the orange. It's comparing the SPT2 and SPT3, which is in blue and purple here, which are the most representative results of the improvement we would have on field, to the orange line. But when we compare it to the original SPT by Mendoza 2013, it was at 120% improvement, a much higher improvement in the SPT results. And we used this 44% in order to be more conservative. But when the expansions of Brasilia happen, the Brasilia subsystem happens, when we perform field trials there, we can be less conservative of this type of improvement. So with these results, we did numeric simulations for the study of the advance length. We did a 3D model. As you can see here, it was estimated that all above the shallow tunnel was grouted because the tunnel it was only 80 meters. The crown was only 8 meters below surface. So we considered that we treated all the collapsible soil above the crown. And this section of the previous tunnel, we use it for the simulation to see what would be the settlement if grouting were used. Was this section S4294 that was located between the shafts PP2 and PP3, where we had the collapsible porous clay of Brasilia, as well as in the experimental field. This work was based in the simulations made by Marques in 2006, and he estimated 5 layers. The first one here is in light green, the last one in dark green, and all of these layers were collapsible porous clay, but it had different properties regarding strength because of the confining pressure was higher in layer 5 than layer 1, so layer 5 has better properties than layer 1. These are, for those who perform simulations, this is the less expected profile of simulation of settlement, where here we can see an extensometer where M1 is the surface, T1 is 5 meters below surface, and T2 is 7.5 meters below surface. So it is expected that T2 is higher than M1. The displacement in T2 nearer to the crown would be higher than M1. But in Brasilia, because of the collapsible nature of the soil, we have a higher M1, 170 millimeters, than T2, that was 150 millimeters. So it was inverted, the settlement profile here in Brasilia. As you can see here, when we use more Coulomb for the simulations, the results were very different. With more Coulomb, we would expect it 110 millimeters, 11 centimeters. But when excavating the tunnel was 170 millimeters. So it was much higher. And when we see the expected values for the for more Coulomb, we can see the inverted profile with M1 lower and T2 higher, but when excavating the tunnel, M1 was higher than T2 because of the collapsible nature of the soil. When the soil collapses in T2, it's like a card castle. So T1 and M1 magnify that collapse. So we have a greater shrinkage, and consequently we have greater volume loss when excavating the soil. Here was the sequential excavation method utilized. It wasn't two numerical machines, since we hadn't had this technology here in Brazil in 1990s, and since it's a greenfield tunnel with not a lot of concern for the buildings, it was built in the sequential excavation method and will be built in sequential excavator method, the expansion, because it's much cheaper and we had more tolerance to the time frame than with the tunneling boring machines. We first calibrated our work with the work of Marques in the work presented. And as we can see here, our simulation is in red and the real settlements are in blue. As we can see, the 3D more Coulomb couldn't capture well these displacements with depth in the in regarding to the main axis, as we saw in the figures before. But when we utilize the hardening soil method, that the hardening soil parameters, and to model our collapsible soil, we almost found perfect agreement with real, with the real results. In red, we can see the 3D hardening soil, and in blue, we can see the actual results. So we calibrated well our model, and later we could implement our grouting. So we use the parameters obtained in the field trials, utilized this hypothesis of similarity of the soils, because the characterization of the soil in S42 and S4294 section and the experimental field were very, very similar. And we utilized this Higgs method implementation is an equivalent method to simulate the grouting. So we utilize a mean expected rigidity value. So performing grouting is much more rigid than soil. So we calculate the equivalent rigidity of the treated soil with this grouting, because grouting not only increases the resistance of the soil, the mechanical characteristics of the soil, but also make it more stiff, more rigid, because they are closely spaced holes with 1 meter between them. The equivalent rigidity of the soil becomes much greater. And this when we are performing simulations to obtain displacement is very important to model. We did these previous simulations of optimization and calibration of our model with the reality, and we variate the excavation steps. What is this? We variated the advance length. In the time, the advance length was 2.4 meters. And we would like to see how the advanced length could be improved with grouting, because not only we will have better results regarding settlement, but we will also pretend to have a greater advanced length, so the tunnel construction can be quicker with an advanced length with a higher advanced length. And the acceptance criteria was from Hung et al. It's a FHWA manual of road tunnels that specify a 1% maximum volume loss. So we specified a maximum 1% volume loss for the next construction of this subway. Here it's a section of the simulation with the equivalent method of implemented, and with as you can see here in blue, in the left hand side in blue, in top left hand side in blue are the grouting. So it are the grout columns, and between this gray, this dark gray and light gray area are the places where we improved the characteristics of the soil. We improved in 44% the characteristics of the soil to mimic the results we have in the experimental field. So here are the results we obtained in our model for different advanced lengths. So with 2.4 advanced lengths, which was the advanced length used in the time of the construction, we would only have 30 millimeters, just 3 centimeters of settlement, of maximum settlement. And we would have only, and with a 4-meter advanced length, we would have 60 millimeters, so 6 centimeters of settlement, and this was the maximum amount of settlement allowed in our acceptance criteria of 1% volume less. So this brown curve represents better the expected settlement and the accepted settlement and the probable advance length allowed. So as we can see, we could have a 66.67% improvement of the advanced length. So we improved from 2.4 meters of advanced length to 4 meters of advanced length, and for a tunnel of 2.5 kilometers, it would result in a much regarding with 2.4 meters of advanced length per day of mean, considering every day 2.4 meters, we would have more than 1,000 days of works, and with 4.0 advanced length of 4.0 meters advanced length, we would have 625 days of work. So it would be an expansion in much less time than the first expansion of the subway system. The settlements were almost 6 times smaller when comparing the same advanced length, and even with 4 meters, we had almost 3 times smaller settlements. So it really improved the performance of our construction, the quality of our tunnel construction. The main limitations, as you probably observed, these were more qualitative than quantitative results, because we had to perform these field trials when works start, because we have to see 1.1 meter grouting is really provides 44%, or we can be more bolder. We can have 120% improvement, or maybe we don't need a 4 meter 4-meter advanced length. Maybe you only need a 3.5 meter advanced length. So maybe we can reduce increase the spacement between grouting holes, maybe 1.5 meters between grouting holes. So these field trials are needed again. We could model better in future works the possible collapse mechanism of the tunnel, because with grouting just above ground, we can have a different kind of mechanism than with the collapsible clay. We could have also vary the sequence of excavation and partialization of the face. So it's a thing that will be done in the design of the subway system, and the support rigidity could be lowered, because since we are having grouting above the support, and the support can be thinner because now we have less stress on the support, maybe we can vary the support rigidity and have a less expensive work, or a less expensive tunnel, since support the support is quite representative of the total value of total cost, of tunnel job. Other solutions could be thought of, like cement churning pile pipe umbrella, the jet grouting pipe umbrella, or maybe compensation grouting. But compensation grouting, in our experience here in Brasilia, wouldn't happen very well, because it it stops the settlement, but doesn't compensate the huge shrinkage of the collapsible soil. So we can't allow our soil to collapse, because later we couldn't compensate the settlement generated by collapse. So the compensation grouting wasn't allowed. So another kind of treatment is CCP pipe umbrella, but it's a more expensive treatment, and it's and as I said in the geotic grouting explanation, only if you have very limited time frames. So the advantage of this solution is that it can be executed before the tunnel work starts. We don't need shaft for this, as in compensation grouting CCP pipe umbrella. We don't need any shaft for performing this grouting. We have less stress on the support, because compensation grouting can have high stress, can provide high stress to the support and make a support more expensive. And it is definitely the most cost-effective method of grouting when time frame isn't an issue in this particular tunnel work. So what we could conclude, that this methodology of performing field trials was very suitable for the next field trials for the Brasilia subway expansion, and we have very, very promising soil improvement results that can be replicated when the tunnel construction began. We had some suggestions for future research and for the field trials, that mainly the grout porous clay adhesion and the expansion of the numerical simulation scenarios. This suggestion number 2 and number 3 were our main concerns. That's it. That's my presentation. Thank you very much for attending. And I really like to quote always Vitor de Mello, a very famous Brazilian engineer, that said that engineering is to decide despite doubts. We had many doubts in this research, and had many doubts in our everyday lives in tunnel construction, and engineering is to deciding despite doubts. Thank you very much. Here you can have my professional email. I would really like to thank the University of Brasilia, Solotrat Engineering, TAIym members, and CBTym members for this opportunity and time with you all. Thank you very much.
Thank you very much, Max, for this wonderful session. It was really a pleasure for us to host you, and very specific information was shared of how the trials were done for the field grouting that was conducted for the project, and how it will be utilized for the project in coming future. Definitely it was an experience and information for young members who have joined, those who have not worked in soft soils, and hope they would have learned a lot from it. Now I would ask participants, if they have any question, they can raise their hand, and they can ask questions from Max. I guess Max heard more. So maybe if you have any more questions, if you think about something you want to ask Max, Max has already told you how to reach him, and yeah, we have one question.
Okay.
From Rahul. Rahul, you could unmute yourself to ask a question, please.
Hello, Sandeep. Am I audible? Hello.
Yes, please go
Am I
ahead.
audible? Hello, Max. It's a good evening from Indian side. I'm Rahul, working in an HPC as a manager civil. I just want to ask that in your grouting, in your umbrella pattern, what kind of dia and length of pipe you used during your umbrella grouting?
The diameter of the grout.
Diameter and length of pipe. Diameter and length of pipe for your umbrella pattern grouting.
The pipe umbrella, we didn't use pipe umbrella. We utilized the Tube-à-manchette technique with a length of 8 meters, because it was the length of the layer, so the depth of the layer, sorry, and the thickness of the layer was 8 meters of the collapsible soil layer above the crown of the tunnel. So we expected to treat all that 8 meters to have similar results as in the numerical simulations.
8 meter.
Yeah, 8 meter, because it was
and
the
picture,
depth of the tunnel.
And the picture you shared is any kind of 3D modeling which you showing settlement simulation?
Yeah, we did Plaxis 3D.
Plaxis 3D. Okay. Thank you.
Okay, thank you.
I think there's one more question from Anshul. Anshul, please shoot your question to Max.
Yeah, thanks, Sandeep. Thank you, Max, for such a wonderful presentation. Just a small query, if you can brief on the pressure regimes used during the TAIym grouting process, because generally we have experienced in India that we usually use a different cycle of pressures when we are going for TAIym grouting. We don't usually go for only one pressure. We adopt increasing pressures at different cycles. So what exactly the methodology you have adopted in Brazil?
Thank you for the question. The development of the pressure isn't linear. So we started with a grouting zero, of course, and then it goes up to 2 megapascals, for example, to open the valve. And when the valve is open, the pressure suddenly drops to the pressure needed by the soil, which we say depends on the groutability of the soil. So, but we utilize it as a criteria that this pressure couldn't be higher than 800 kPa, because we didn't want to fracture the soil. So we limited the maximum grouting pressure, but the grouting pressure varied based on the type of soil we were treating. So the pressure wasn't linear.
Okay, understood. Thank you.
I think that's all we have for today. I'll just go through some of the announcements for upcoming events in Tunneling Association of India Young Members before concluding this event. So our next webinar from Switzerland will be sharing his experiences, and he's a very well-known personality and has a lot of books and contracts. And he will introduce the ITA form of contract for underground works, which is also known as the Emerald Book. Then we have several other webinars lined up, which are various collaborations with Canada, Japan. We already shared with the webinar as well. We'll be looking forward after this webinar to collaborating forward and more exchanges in coming future. Then we will be inviting one of the session data on the role of industry in India. And as you know, you must have received an email for the new edition, which is out and has a summary of members have done in year and how we are going to take this forward. Then welcome to participate and become active in helping the committee to do all this work. If you're interested, drop it to the email ID of TAIym. We know that World Tunnel Race 2020 are going to SITA is on September 2020, and we all know when World WTC 2020 is. And it's kind of play a part in regional development of mining industry in Asia. So stay tuned. More information will be shared how to join the symposium. And I say goodbye. I would like Brazil, Young Members Group, for allowing us to have such a wonderful collaboration, and would like to thank Max for taking out his time, sharing his wonderful experiences with us. And again, would like to thank Alex and his team for being so prompt in responding to our proposals and working with us hand in hand to make this possible. This is wonderful how two different countries come together and share what they are doing in their respective countries, and we find so many similarities and learn from the differences as well. Thank you very much. Thank you, Max. Thank you, Alex.
Thank you,
And
Sandeep. It was
thank you,
wonderful.
everyone, for attending. Thank you very much.
Thank you, Sandeep. It's a pleasure.